So this is the lecture for Chapter 7, which covers the quantum mechanical model of the atom. The pages of the text that this information comes from is shown right here on this slide. Please make sure you're reading and outlining the text pages before you watch this lecture. We're going to start with describing electrons. Electrons are a part of an atom, and they are very, very, very small. A single speck of dust has more electrons than the number of people who have ever lived on the Earth, on this planet, from the time that people first existed. This gives you a little idea of how many electrons there are just in the universe and how very small they are. We're talking about, if we're talking about a handful of salt, that is more electrons, I think, than you can even count. Why we pay attention to these electrons is because electron behavior determines the behavior of the atom. Why sodium explodes when exposed to air is due to the arrangement and the number of electrons that sodium atoms have. Same goes with the noble gases. The reason why they are noble is because of the way their electrons are arranged. So therefore, it's very important for us to know about this arrangement because it allows us to do a lot of things with the atoms, including predicting how an atom is going to behave. The difficult part is that it is impossible to actually see electrons. We have never seen an atom. We do not have microscopes capable of getting that small. Any information that we get about electrons comes from computers and measurements and experiments that kind of involve pinging laser beams, if you want to think about that, off of the electrons and getting readings back. We've never actually seen them. So most of the information that we have about electrons comes from measurements in the macroscopic world that we then make theoretical guesses about how electrons are actually behaving in the atom. The quantum mechanical model is the most recent model of the atom that we have. If you remember, we were talking about Rutherford's nuclear model, then we went to the Bohr's model, which we're going to talk about later. But the quantum mechanical model is the most modern model. Its main difference from the other models is that it explains the behavior and existence and placement of the electrons. So it really gives us information about where the electrons are and how they behave. One big thing is that it allows us to predict properties. So if something is in the noble gas column, we are able to predict that it is going to be relatively unreactive because we know information about the behavior of their electrons. Other examples are why some elements are metals, why others are nonmetals, why some are solid, why some are gas. It tells us about ions that form. Why is it that group 1A forms +1 ions? And other properties of the elements, other periodic properties that we're going to talk about in Chapter 8, including reactivity, activation energy, electronegativity, and so forth. Light and all energy in the universe is encompassed in what we call the electromagnetic radiation or the electromagnetic spectrum. It's every kind of energy that you have ever observed or heard about. Energy, remember, is technically not matter. It does not have mass. So it is a different form of planetary molecules. It's actually energy. It's a whole separate thing from matter. All electromagnetic radiation is composed of waves, what we call oscillate, meaning they just kind of go back and forth. Now these waves function in two separate fields, an electric field and a magnetic field. An electric field is just where you have electrically charged particles, and a magnetic field is where you have magnetized particles. So when we think about magnetic field, we're talking about the north and south pole, the magnetic field of the Earth. That's why compasses face north. And these waves actually function in both of those planes. I'm going to show you a picture in 1 second where we're going to talk about that a little bit more. One very important characteristic of electromagnetic radiation, besides the fact that it travels as a wave, is because it travels like a wave, it's going to move at the same speed. All electromagnetic waves travel at 3 times 10 to the 8th meters per second, which we call the speed of light. This is a constant. This is technically the speed in a vacuum, but again, we can use this to estimate the behavior of waves, assuming that it's not in a vacuum, but we can still use that as an estimation. All waves, no matter if they're gamma radiation, microwaves, travel at this speed. So if we look at the speed of waves, this is a perfect example, is fireworks. Speed of light or waves or any of electromagnetic radiation is so fast, we have not been able to travel nearly close to this speed 3 times 10 to the 8th meters per second is extremely fast. Just to give you a little sense of how fast the speed of sound is 340 meters per second. We have gone the speed of sound. That's where we talk about the Mach 3 and those kind of things. This slide is also showing you why when you watch fireworks or if you hear, during a thunderstorm, why you see the fireworks and then you hear the sound. It's because the light is traveling so much faster than the sound. This graphic is showing you the magnetic and electric field components. So if we look at the wave here, this is it's oscillating, meaning it's going up and down. And the red is it's oscillating through the electric field. The blue is it oscillating through the magnetic field. Notice the wave has all the same characteristics. It has the same height. It has the same frequency and wavelength, which we'll talk about in a second. It's moving in the same direction. It's just being affected by two separate fields. This will affect its motion, its frequency, its wavelength. This really gets into a lot of theoretical, and actually it's a lot of physics involved here. So if you just understand that the wave is actually traveling through two separate fields the exact same way, but there's actually two separate components acting on the wave. Since all waves travel at the same speed, other components are what differentiate them from each other. One of those things is called amplitude. Its abbreviation is A. This is the height of the wave. So from the origin, or what we call the middle of the wave. So from the origin to the top, which is called the crest, or the origin to the bottom, which is called the trough. Amplitude actually tells you how intense the light is or how bright it is. Wavelength symbol is a Greek letter lambda. It looks like an upside down Y. This is the distance covered by the wave. This is different than speed. This is basically how far apart the tops of the waves are or the bottoms of the waves are. So we can say from crest to crest or trough to trough. So if we look here, it's just showing you wavelength and amplitude. Notice the origin is the middle of the wave. So the amplitude is how high the wave goes from the top and from the bottom. And the wavelength is either from top to top or bottom to bottom. Probably the most important characteristic of a wave is frequency. And this can have two separate symbols. It can be a nu, we call a nu, which is looks like this kind of cursive V. That's a Greek letter again, or N. This is the number of waves that pass a given point in time. So if we just look at this point here in a wave, and we count how many times the wave cycles through, that would be frequency. Frequency is a measure of the number of waves per second, or number of cycles of the wave. So that governs the unit. The unit of a frequency wave, the SI unit, is a hertz, which stands for 1 cycle per second. So you can also write a hertz as second to the negative first. Nodes are points of zero amplitude or equilibrium position in the wave. So if we go back to this graphic again, here's a node right here. A node, a node, a node. So you can count how many times the wave is passing through that point. The total energy is proportional to the amplitude and frequency. So when we talk about what is the difference between a gamma radiation wave and a microwave, for example, we're talking really about the frequency and the amplitude. The larger the amplitude, the more force the wave has. Again, the brighter, also if we're talking about light. And the more frequently the waves strike, the higher the frequency, the more energy it carries. In general, frequency and wavelength are what we call inversely proportional, which means they're opposite. So as wavelength goes up, frequency goes down and vice versa. Because of this relationship and because of the speed of light, we actually can use an equation that's shown here, which involves the frequency, the wavelength, and the speed of light. In parentheses here is just the units. And this can be used to calculate the wavelength or frequency when given one or the other. So if we look at this sample problem, it says calculate the wavelength of red light with a frequency of 4.62 times 10 to the 14th second to the negative first. So if I'm only given frequency in the problem, which I wrote down here, and it's asking for wavelength, I'm immediately going to know my formula is C equals lambda V. This is the speed of light equation. C is constant, so you're always going to know that number is 3 times 10 to the 8th. And the units for the speed of light are what govern the units for the problem. So if we look, it has a second as the denominator, which matches up with a hertz, but the wavelength needs to be in meters. Now I put there nanometers, which is what wavelength is usually measured in, but when you do this problem first, the actual answer is always going to come out to be meters. So all I did here is plug my numbers in below, and I solve for wavelength lambda, and I get this answer. Again, because you use speed of light, which is measured in meters, your answer is going to come out in meters. Wavelength is usually measured in nanometers, which the relationship is 1 meter is 10 to the ninth nanometers. So all I do here is convert. When you put this in your calculator, you have to put 1 times 10 to the ninth. And I get a final answer of 6.49 times 10 to the second nanometers. And if you wanted to leave that as 649, that would be fine as well. Another sample problem would be calculate the wavelength in meters of a radio signal frequency of 100.7 megahertz. So again, I'm given a frequency, I'm looking for a wavelength, so I know it's going to be the speed of light equation. So here's my constant for the speed of light. Now, frequency is given in megahertz, and because here it's second to the negative first, that has to be the unit in order to use 3 times 10 to the 8th. I have to convert megahertz to hertz. The relationship is 1 megahertz equals 10 to the 6 hertz. So I solve there first to get the answer of wavelength in hertz, and then I plug in, solve for wavelength to be 2.98 meters. Color or visible light is everything we see. We think we see a lot, and we do. Our world is composed of many, many images, but we see a very, very small fraction of all the energy available. So color is what we see with visible light. Color is directly determined by the wavelength or frequency of the light that you are looking at. So if we look at white light, this is light produced by lamps. A lot of sunlight is white light. We call that a continuous spectrum because it contains all the colors. Roy G. Biv tells you all the colors that exist: red, orange, yellow, green, blue, indigo, and violet. All the other colors are actually just a combination of those. So when you see light, when you see a color of something, if you're looking at a red wall, for example, what's happening is the white light is hitting the red wall, and the red pigment in the paint is absorbing all colors but the red wavelength, and the red wavelength wave is actually being reflected by the wall, and that's what your eye is picking up. Your eye has lots of sensors in it. It has something called a retina that sends a signal to your brain, and your brain interprets what you're seeing as red light. So a rainbow actually has all the red light colors. That's why we call it a continuous spectrum. But when you see a specific color, that's what's being reflected by that object. If we look at the effect of amplitude and wavelength on color, wavelength again tells you the certain color. So is it going to be red, yellow, blue? You see the different distances between the waves. And amplitude tells you the brightness. So if we look here, this amplitude is not as high as this amplitude. And amplitude is going to tell you, bright red versus a dull red. It can even have to do with the neon colors, for example. This is showing you the entire electromagnetic spectrum, from radio waves, microwaves, infrared, visible light, all the way up to gamma. It's going to be arranged by wavelength and frequency, and they're going to go in opposite directions. So if you look here, the frequency is actually increasing, and at the same time, the wavelength is decreasing, or it's increasing to the left. It would be a good idea for you to know the order of the electromagnetic spectrum in terms of energy. Not really the specific frequencies, but if you just know that radio is the lowest energy, then microwaves, then infrared, and all the way up to gamma, that would probably be a good idea. Again, if you see here, the very small portion of visible light that we actually see. So imagine what else is out there that we don't see. There are some animals that can see into the ultraviolet and into the infrared spectrum. And there's definitely cameras and lenses and computer programs now that allow us to see these different spectrums. But all we see is that small portion of visible light within that wavelength. Again, white light is what we call a continuous spectrum. A rainbow is a continuous spectrum. If you notice, the colors all blend. There is no wavelength and frequency not represented here in white light. All the colors blend together, and that's what we call a continuous spectrum. Visible light, again, is only a very small fraction of the electromagnetic spectrum. We have radio waves, gamma rays, infrared, all the waves you saw there. If we talk about in terms of energy, radio is the least, gamma is the highest, and again, you probably should know that order. When we say that radio waves are the lowest energy, which means we mean that they have the highest wavelength and the shortest frequency. Remember that wavelength and frequency are opposite. Frequency and energy are direct, so they are the same thing. Some high energy electromagnetic radiation is damaging to biological molecules and therefore living things. For example, gamma rays are a very strong form of radiation. This is what comes off of nuclear bombs, and this can cause major damage to human and animal cells. This is just showing you a little bit of infrared. Infrared's to the left of visible light. It's a little less energetic than visible light. It's what we think of when we think of heat signatures. So you can look here, it's 3 dogs and a man. You can see where the heat is on these creatures. You'll see these sometimes in ghost hunts. We actually use some form of electromagnetic radiation to kill cancer cells. We call it radiation. Um, the good thing about radiation treatments is it can be very specific to just hit the tumor. So if you see in this picture, all the healthy tissue surrounding the tumor is not getting the radiation. It is just the tumor that is getting kind of a laser beam of radiation. Whereas if we think of chemotherapy, which is the other major treatment of cancer, that actually affects all the cells. You kind of take poison and kill all the cells, hoping that the most cells that are killed are the tumor cells. But radiation here actually will shrink tumors. Usually what they use radiation for is to shrink a tumor and then surgically remove it. So if there's, you hear people say a golf ball sized tumor, a softball sized tumor, they'll use radiation to shrink it and then surgically remove it. We're getting into now a little bit of physics that have to do with the way light behaves. Light and sound and things are also physics topics. I told you a lot of times it's going to overlap. What we're going to talk about is the wave nature of light and electromagnetic radiation and how it behaves. When waves interact, and we're talking any kind of wave, this can be sound as well, we call that interference. Yes, that's a sports term. Interference is not always bad. There's actually 2 types of interference. There's constructive interference and destructive interference, and the names kind of tell you what they do. When you think of constructive interference, sometimes I think of constructive criticism, which is suggestions that's supposed to make you better, whatever you're trying to do. So constructive interference are waves that interact in a way that makes a wave larger. What we say is that the waves are in phase or kind of in the same range as far as when they're going up and when they're going down. Destructive interference is when the waves cancel each other out. The waves are out of phase. So if you look at this picture and we look at these 2 waves that basically are coming in contact with each other, you can see here they're exactly in sync, or what we say in phase. They are going up and down at the exact same moment. So when that happens, we get constructive interference, and you actually get a wave that's twice as large as the original wave. It's kind of like they combine forces to make a bigger wave. Down here we see waves that are out of sync or out of phase. You can see they're exact opposites. When that happens, basically it's like adding +3 and -3. You end up with 0. So destructive interference is when the wave completely cancels out all of its wavelength or frequency. It's basically you get a straight line. Now, of course, you can have different degrees of this. You can have waves that are slightly in sync, waves that are slightly out of sync. But really, for this chapter, that's more physics-based knowledge. If you just understand the difference between constructive and destructive, that is good. Diffraction is the ability of waves to bend. So when we think of waves, they're actually able to travel through obstacles and barriers, and the entire wave is able to move through. Particles can't do this. So if we talk about using light, which is a wave, and putting it through a split, or like if you have a piece of cardboard and you have 2 holes in it, the light will actually bend around and the entire light will be able to come out. And we get something called an interference pattern. Remember that light actually has 2 parts. It has a wave nature and a particle nature. So this is showing you when waves hit, so if we're talking about, a light source going here and here's the slit, it's actually able to kind of, if you think about it, almost like taking a piece of paper and pulling it through a hole, you're actually able to get the whole thing through the slit, and then it kind of goes back out and starts to expand until it's back to its original size. We call that diffraction. The wave is able to actually diffract and bend through that slit. Particles, on the other hand, can't do that. If you were taking, for example, a hose and shooting it at a piece of cardboard with a small hole, the particles, water particles that are able to get through the slit will go straight through, but the rest of them are going to do nothing but fall to the bottom. They can't bend or diffract the way that waves do. This picture is showing you how a light would behave when you have 2 slit interference, when you have bending. The first thing would be the particle nature. Remember, the particle is not going to go through. So really all we're talking about here is the wave nature of light. So if we see the beam or the waves coming towards the slit, it actually separates into 2 separate beams now. But eventually these waves, you see these patterns, they're going to come and interact with each other. They're going to come back to each other again. And what happens when they come back and interfere with each other again, whether it's constructive or destructive, depends on where in phase the waves are. So we see this top one here, the dark spots is what this is talking about. When you see the dark spots here, you're getting destructive interference. The waves are exactly opposite each other, so you're getting a straight line. That straight line doesn't have a wavelength or frequency, so you see it or you interpret it as a blank spot or dark spot. If we have the waves that are in phase, again, they kind of double up, they power up each other, and you get a nice bright spot right here. So this is what happens after you put the light through a slit, and then it comes back together again. The photoelectric effect is very interesting, and it's really interesting now because this is how solar panels work, is with the solar photoelectric effect. When you have a metal, remember that metal bonds are very unique. We call them the C of valence electrons model. The electrons aren't held as tightly. So when you have a piece of metal with light shining on it, what can happen is the light beam can be carrying enough energy to break the bond between the electron and the nucleus, and therefore the electron is actually what we call shot off. Classic wave theory tells us that light energy should be able to be transferred to this electron, and it should be able to pop off on all ranges of light. We call this ejection of electrons. Remember that the energy of a wave is directly proportional to its amplitude and frequency. So what ends up happening is a dim light, a bright light, and the color of light all affect whether or not an electron is actually released. People have done experiments with this using, for example, different colors of light, different brightnesses of light to figure out when the electron is released and when it's not. So this is just showing you the experiment. This is what happens with a solar panel. You have a sheet of metal, the light is hitting it, the electrons are emitted, these electrons are gathered, and then they're turned into energy. This experiment is showing you when exactly the electrons will be emitted. In these experiments, scientists figured out there was a maximum wavelength for electrons to be emitted. Not all wavelength, not all colors of light will release these electrons. For example, red light will not do this. We call this the threshold frequency. That is kind of the point where electrons will no longer be released. It doesn't matter the intensity or the brightness. We can have a very bright red light. It's just not carrying enough frequency to break the bond between the electron and the nucleus. Lag time is just something about the time between the light shining on the surface and the electron being ejected. It's just talking about the relationship between the frequency and the brightness of the light and how that affects electrons being emitted. Einstein came up with an idea of photons. This is related to quanta or quantum, but he uses the main word of photon. A photon is just very simply an energy packet. You can think of it like an electron that has been released traveling through space. So that's what a photon is, essentially just a free electron. The energy of a photon is directly related to its frequency. The higher the frequency, the higher the energy, and it's opposite the wavelength. The proportion of that is called Planck's constant. Its abbreviation is H, and its value is 6.626 times 10 to the negative 34th joule seconds. That is another known that you will have to know. So here's the equation that uses Planck's constant. It's E equals HV, E for energy, H is Planck's constant, V or nu is frequency. And then if you don't have frequency, you can actually use it for wavelength as well by doing H times C over lambda. The fact that Planck's constant is measured in joules, again, dictates the type of units you can use. For example, any mass would have to be in kilograms because you're using a joule. So an example problem, calculate the number of photons in a laser pulse with a wavelength of 337 nanometers and a total energy of 3.83 millijoules. So the first equation I'm going to use is the energy of a photon equals Planck's constant, and this time, since I'm giving a wavelength, I'm going to do hc over lambda. Remember that since you're using c, speed of light, the wavelength has to be in meters, so I'm converting that here. And I'm simply multiplying and solving for the energy of a single photon, which is 5.899 times 10 to the negative 19th joules. This question asks for the total energy, so I'm going to have a second equation here, which is the number of photons equals the total energy over the energy of a single photon. So I'm going to use this to calculate how many photons there are with that energy. So I first changed 3.83 millijoules to joules to make sure the units are the same. A millijoule is just a normal milli, it's a third. Then I divided those two numbers to get the number of photons to be 6.49 times 10 to the 15th. Second problem, what is the frequency of radiation required to supply 1 times 10 to the second joules of energy from 8.5 times 10 to the 27th photons? So I'm going to use that equation from before, E photon equals E total over number of photons. Notice it's just a rearrangement of this equation. You can rearrange it however you need to use it. And then I'm going to rearrange Planck's constant equation to get frequency equals the energy over Planck's constant. So first I'm going to plug in my E total from the problem, which is 1 times 10 to the second, and the energy or the number of photons, 8.5 times 10 to the 27th, to get the total energy of a photon. From there I'm going to plug that into this equation, divided by Planck's constant, to get the frequency, which is 1.8 times 10 to the 7th hertz, or second to the negative first. Once a photon has a threshold frequency for an electron to escape, it is released. We say that this is related to what we call the binding energy. So the binding energy is the energy needed to bind an electron to the nucleus. Sometimes when you have higher frequencies of light, the electron absorbs more energy than is necessary to escape. It's like it gets such a big pulse of energy that it has more than it needs. This excess energy then helps speed up the movement of the electron after it has been ejected. So we say the excess energy becomes kinetic energy. And to figure out how much kinetic energy, we figure out the energy of a photon minus the binding energy. And anything left over actually is the kinetic energy that speeds up the movement of the electrons. When atoms or molecules absorb energy, that energy is often released in the form of light. So we see this fireworks, neon lights, lots of different things. When light passes through a prism, it is what we call diffracted to see a pattern or the emission spectra of a specific element. This is a non-continuous spectrum. Remember, rainbows are continuous, emission spectra are non-continuous, which means not every wavelength and frequency, not every color is represented. We can actually use this kind of like fingerprints to determine the identity of a material. We call this flame tests. Rydberg analyzed hydrogen's emission spectrum and found that you can actually use an equation to figure out how much energy is present when an electron moves between orbitals. This equation is 1 over wavelength, which would tell you the color, equals 1.097 times 10 to the 7th, and then n stands for the principal quantum number. So we're talking about what orbital it's in. So if you look at emission spectra, you would have a hydrogen lamp here. It's kind of like a neon light. You're going to need some kind of prism or diffraction gradient to separate the light. But when that happens, you see the component colors. You see what colors or what wavelengths and frequency that particular light is made of. And you can see them here in the emission spectra as different straight lines of light. Again, this can be used to identify elements because each element pretty much has its own separate emission spectra, kind of like a fingerprint. One thing to notice here is that there is just individual lines of color that are pretty far spaced apart. It's not like a rainbow where you see all the colors straight through. This is just showing the different lamps and tubes that you can get to have these different elements in them. Any kind of gas can do this. This is actually how neon lights work. So this is just some examples of spectra. You can see they pretty much all have their own mark or fingerprint, different kind of spectra that can be used to identify different elements. Sometimes they have just a few lines of color. Sometimes down here they have very numerous amounts of color, very numerous lines. If you think about in terms of the number of electrons that can move, the number of electron transitions, helium only has 2 electrons, where neon has much more than that. And that pretty much tells you why there's that many more lines for neon than for helium. A flame test is actually going to give you a solid color because you're seeing many electron transitions at a time. If you use a diffraction gradient, you can actually see the emission spectra here, but these are just a few elements, salts. Basically, if you light on fire, you're going to get these different colors. Emission versus absorption are actually exact opposites. Emission is what's going out, absorption is what's going in. So we just talked about the way color works is the white light absorbs all frequencies of color except for the color that you're seeing. So they're actually exact opposites. So if you see these two, the top is the emission, the bottom is the absorption, and you can see they're mirror images of each other. The emission consists of only the colors that are reflected. The absorption is the colors that are absorbed. And you can see the positions where the color is reflected is actually shown here in blank or black spots. Bohr's model is not a correct model of the atom, but we use it a lot because it's very easy to see electron transitions and it's very easy to teach orbitals. And so it's still used sometimes, but we know the quantum mechanical model is still the most correct model. The Bohr model proposed that electrons have very specific amount of energy that again Bohr called quantum. He was the first to define what an orbital is. His version of an orbital is these very fixed orbits, kind of like the way the planets travel around the sun, that are a fixed distance from a nucleus, kind of like a train track. The electron is stuck on this track, and that the electron is proportional to the distance away the orbital is from the nucleus. The farther out you go, the more energy is contained in that orbital. When electrons jump or they become excited, they can go up to a higher orbital than they should be. Ground state is where the electron should be. It's when they're as close to the nucleus as possible. Excited state is when the electron has jumped. It has absorbed some energy and jumped up higher than it should be. The distance between the orbital, or how far the electron jumps, tells you about the frequency and energy being carried by the photon that's released. So if we look at this is a Bohr model of an atom. You can see the orbitals here. Here's the nucleus. So the first ring, we have the quantum number of n equals 1. Second ring's n equals 2, n equals 3, and so on. So if we see here, the electron is the yellow. In its ground state, or closest to the nucleus it should be about here in the first one. But these electrons are all excited, and they're all falling a different distance. They fall because they're unstable, and depending on how far the electron falls, is going to give you different colors of light. And this is where the emission spectra comes from. And you can see, we know that violet light contains more energy than red light, and the violet electron transition is actually farther than the red, which makes sense. de Broglie came in after Bohr's model was made and said that electrons have to be moving like waves. He basically figured out that if you see color when you do a flame test, for example, we know color comes from from frequency and wavelength. So if an electron is having a color, it has a frequency and wavelength, therefore it has to be moving like a wave. The wave character of the electrons is actually very small, so it is more significant. For example, if you have a softball or a baseball and you throw it, that actually is moving like a wave, but the wave amplitude or how much the baseball is moving is so small compared to the size of the baseball, you don't really notice it. But since an electron is so small, you actually are going to notice the wave character more. De Broglie did some experiments with electron beams going through slits, and he figured out these nodes and patterns. He came up with the idea that the electrons are not moving like in train tracks. They're not moving like orbits like the planets around the sun, like Bohr said. He said they're actually moving like waves. He came up with an equation which is lambda equals h over mass times velocity, and this is telling you the particle speed, or it's going to give you actually eventually the wavelength, but it takes into effect the mass and the velocity. Notice the mass has to be in kilograms. That's because h eventually has joules in it, and that's why you need it in kilograms. So this is showing you electron diffraction with the particles. Notice the particles that do not move through the slit do not go through the other side. It's really only ones that can fit through the slit. That's the way particle behaves. But since light is a wave, the entire light is able to go through the slit. If electrons behave like particles, there should only be 2 bright spots in the target. And since it's going to actually behave like light, there was not. Electrons actually present interference patterns showing that they behave like waves. So to calculate the wavelength of an electron traveling at 2.65 times 10 to the 6 meters per second, we're going to use that equation we just looked at. Lambda equals h over mv. Lambda is going to be the wavelength in meters. H is Planck's constant. M is the mass of a single electron. This is something you may need to know. It's in kilograms here. And then v is the velocity. So I'm going to multiply and divide and solve, and I get the wavelength to be 2.74 times 10 to the negative 10th meters. We know that electrons make up, or photons make up, electromagnetic radiation. And we know radiation, including visible light, has both a particle and wave-like nature. These two things have conflicting properties. For example, the wave nature of light tells you there should be an interference pattern. The particle nature does not interfere, does not diffract around a slit. Because they do two different things, you can actually observe them separately, and it gives you even more information about how how the electrons behave. The particle nature can tell you the position or where the electrons are when they're passing through the slit. The wave and particle nature of electrons are complementary properties. The more you know about one, the less you know about the other. This hooks into Heisenberg's uncertainty principle, which says that the product of the uncertainties in both the position and speed of a particle is inversely proportional to the mass. So what Heisenberg essentially said is the act of measuring the particle and wave-like natures of an electron change one or the other. So if you know about the particle nature, you know less about the wave nature. If you know about the wave nature, you know less about the particle nature. So what he said is there's inherent certainty with any measurements you take of electrons. This certainty is inversely proportional to the electron's mass. So what he's saying is the more accurately you know the position of a small particle, the less you know about its speed. Notice it says small. So the smaller the particle, the more this is effective. So, if we're talking about your car is very big. There's not as much uncertainty with a big object as there is a small object. So if we look at this uncertainty principle as far as the light here, we have the electron source moving through slits. Any experiment designed to observe the electron results in detection of a single electron particle and no interference pattern. So if we look here, you're going to have the beam of electrons are actually moving through. So the more you know about the particle nature, the less you know about the wave nature, and vice versa. According to classical physics, particles move in a path determined by the particle's velocity, position, and forces acting on it. Determinacy is the definite, predictable future of an object. They use this all the time in physics. They try to predict what's going to happen. For example, when a plane goes up in the air, they would really like to know what's going to happen to the plane. But because of Heisenberg's uncertainty principle that says you cannot know the exact position and velocity of an electron at the same time, you cannot predict an electron's path. We say the electron has indeterminacy. You cannot tell where the electron is going to be in the future. So the best we do, and what the quantum mechanical model does, is describe the probability of finding an electron at a particular location. You never track a specific electron. So we're not going to say this is electron 1-A and we're going to follow its path around the nucleus. We cannot do that. What we can do is say in this orbital there probably will be two electrons all the time. Doesn't matter what those two electrons are, there just will be two there. So we talk about trajectory versus probability. Baseball, we talk about hitting a baseball with a bat. You can actually in physics track the exact path of that baseball. So at any moment along the trajectory, we can predict where the baseball is going to be. That is actually how they figure out how high those nets need to be behind the dugout to protect people, etc., and so forth. When we talk about the quantum mechanical, the uncertainty, the indeterminacy, this is saying the electron can be in any of these positions as you move from left to right here. So we see the difference. This is a very direct, classic, predictable path, and then here, this electron could be any of these places. This is a very broad category. And this really shows you a great example of this would be Bohr's model. This is the quantum mechanical model. The quantum mechanical model does not give you a specific of where an electron should be. It tells you more about where the electron isn't sometimes than where the electron is. Electron energy and position are complementary. So for an electron with a given energy, the best we can do is describe a region of high probability of finding that electron, and that's what the quantum mechanical model defines an orbital to be. It is a probable location of finding an electron. Remember, it's not the specific electron. It is not electron 1-A. It is any electron. A probability distribution map of a region where the electron is likely to be found is another way of thinking of an orbital. Many of the properties of the atoms are related to the energies and where these electrons are, in which orbital the electrons are positioned. Some calculations have shown us that the size, shape, and orientation of the orbital are determined by three integer terms of the wave function, which are here. We call these integers quantum numbers. So we talk about the principal quantum number, the angular momentum quantum number, and the magnetic quantum number. So the principal quantum number, n, characterizes the energy of an electron in a particular orbital. They correspond directly to Bohr's integers. So n can be an integer 1 to 7. So the larger the value of n, the more energy the orbital has. The energies are defined as being negative because an electron would have zero energy when it escapes the atom. So basically, if you want an electron to be separated, you always have to put energy in because the energy is going to be negative. The larger the value of n, the larger the orbital. Actually, the bigger the orbital is as well. And as you get larger, the amount of energy between orbitals gets smaller. So if we look here, the equation E sub n stands for the principal quantum number, is equal to negative 2.18 times 10 to the negative 18th joules over 1 over n squared. This tells you the energy contained in each orbital. So if we look here, this is just calculated each one. So we see the n equals 1 principal quantum number, n equals 2, 3, and 4. Notice the space between the orbitals is getting smaller as you go up in energy. And this is just the individual energies of each orbital. You can see that they're going to get bigger, and you can see that they're negative. In order to transition to a higher energy state, the electron must gain the correct amount of energy corresponding to the difference between final and initial state. So if an electron wants to jump from the 1 to the 2 orbital, it needs to gain the amount of energy that's the difference between the 1 and the 2, these two numbers here. Electrons in higher energy states are unstable, and they tend to lose the energy and transition back down to the lower or ground state. When this happens, a photon is released, and the energy carried by this photon is directly related to the energy difference between the two orbitals. This is what makes emission spectra, and this is what tells you about electron transitions. So if you look at this picture here, N1 is the ground state. If an electron absorbs energy, it can jump up into the n equals 3 orbital. This is an excited state. The excited state is unstable, so the electron will fall back down, and then light, in terms of a photon, will be released as a result. The wavelengths of the lines in the emission spectrum can be predicted by calculating the differences of energies of the states. So if you look at the equation here, the energy of the photon released is equal to the negative change in energy, or energy between the orbitals, or E final equals minus E initial. If we substitute hc over lambda, we get the final equation here, which is negative 2.18 times 10 to the negative 18th over 1 n final squared minus 1 over n initial squared. So if we look at all these transitions, the different orbitals are listed here. We can talk about the electrons moving up and down and traveling at different wavelengths and landing in different spots in the hydrogen atom orbitals. So if we look here, if electrons, notice, doesn't matter where they start, but if an electron lands in the n equals 1 orbital in a hydrogen, you're going to get an ultraviolet wave released. If the electron ends in the n equals 3, you're going to get infrared. And if the electron lands in the n equals 2, you get visible light. These are all called series, electron transition series. So the next problem is calculate the wavelength of light emitted when the hydrogen electron transitions from the n equals 6 to the n equals 5 orbital. So we're going to use that equation we talked about before, E equals negative RH times 1 over the final orbital minus 1 over the initial orbital. So we're going to do negative 2.18 times 10 to the negative 18th, that is a constant, over 1 over 5 squared minus 1 over 6 squared. This is going to give us the energy of negative 2.66 times 10 to the negative 20th joules. This is just switching the sign to make sure that the energy the photon is carrying is positive. You can kind of think of it as it's a difference, so it's going to be an absolute value, so it's always going to be positive. And then I'm going to plug that into the wavelength equation, hc over E. Take that number and plug it in here and solve for 7.46 times 10 to the negative 6 meters. So this number here tells you the energy carried in the transition, and this number here tells you a little bit about what type of radiation is going to be released. Y squared is the probability density. It's telling you the probability of finding an electron at a particular point in space. This number decreases as you move away from the nucleus. The radial distribution function represents the total probability at a distance of finding an electron at that distance. Nodes, again, are where this probability drops to 0. So if we look here, I showed you this before, it's basically where the wave hits a line of origin. So here's a node, here's a node, here's a node. So this is showing you the 1s orbital. Again, it is not a train track. It is a region of space. So if we look at these dots as a density diagram, these are all the places where an electron has been observed. And if we look at the region where the dots are the densest, that can be thought of as an orbital. This is talking about the radius from the nucleus and how far away it can get before the probability goes back down. So if we look here, this is the distance from the nucleus. This is the total radial probability. The max is 52.9. And we see right here the 200 picometers from the nucleus is the max. It's basically the border of the 1s orbital. The quantum number L determines the shape of an orbital. L can have a value of 0 to n minus 1. Basically, an s orbital has a value of 0, p has a value of 1, and it goes up from there. Each value is called by a particular letter that designates the shape. So the four most common there is S, P, D, and F. There is a G and H, but you are very unlikely to see those. An s orbital is spherical. A p orbital is like a dumbbell or two balloons tied together. A d is like four balloons tied together, and an f is like 8 balloons tied together. So the s orbital has a value of L equals 1. It is a spherical shape. It is the lowest energy orbital in a state, and its nodes are n minus 1. So if it's a 1s orbital, it has 0 nodes. The 2s and the 3s get slightly larger as they go up. So 1s has less energy than the 2s, so on and so forth. So this is just telling you about the nodes and where they occur in the orbitals. L equals 1 is the P. Remember, the P is like a dumbbell. The P actually is made up of 3 different orbitals that point along the 3 axes, X, Y, and Z, and they are labeled as such. It is the second lowest energy. It is 2-lobed. The nodes of the nucleus is equal to n. So if we look here, here's the axes. There's X, Y, and Z, and the P orbitals just follow along of those axes. L equals 2 is the D orbital. There are actually 5 different regions where the D orbital exists, 5 different planes. These are labeled dxy, dyz, dxz, and then dx squared and dy squared. They are mainly 4-lobed, and they actually have planar nodes. They're actually in a very interesting arrangement. So if we look at the D is in between the X and the Y, that's where that name comes from. They're not actually along the X, Y, and Z like the P are, they're actually in between. The L equals 3 is the F orbitals. There are 7 different arrangements. Again, these are kind of arranged on the planar, so they have very different shapes. There's actually a video that I've posted that you can see these kind of working together and how they kind of overlap with each other. So this is what all these orbitals combined look like. This is why atoms are spherical in nature. They all kind of blend in, almost like a flower arrangement in some ways. They fill in the gaps of the other orbitals. This just tells you the different energy levels and the sublevels and orbital specifications that exist. So in the first level, there's only 1 sublevel. Second, there's 2 sublevels. 3, there's 3 sublevels. 4, there's 4. And just telling you the different orientations. These are the quantum numbers. And that concludes our lecture for Chapter 7.